So while plots are the basic building block for everything we do, we also extend from plots to formal testing. So there are a few steps in the formal testing process, and the way that I have always thought about it is that the first step is the visual plot. So the visual plot informs our thinking about what we're doing, and it gives us an informed position to proceed with for a formal statistical test. I think that without the plotting part of this process, you may set up the wrong test or you can do some strange things. So first step is going to be the plot, and that's going to be a recurring feature in the way that I set your assessment questions. The next part of the process is to formally specify a null and alternate hypothesis. So for us, there are a few ways that you can do this, but we're going to follow a fixed format because we're just getting started. So we're learning to drive is the analogy that I like to use. So these are the basic rules that will get us most of where we want to go. They'll make us safe people to drive the statistical software. When we set a null and an alternate, we have to set something which is called the certainty level for our decision making. We're going to go over this a few times. So at the moment, I just want to say we're going to use alpha, which is how we define our certainty level, of 0.05 or 5%. So I'll explain in some subsequent lectures really what that means. So for the moment, we just need to know that this is a step. Then we conduct the test. Now, the tests that we use are based on statistical tests that use distributions. Well, for the most part, the tests that we use. And these distributions follow something that we know. And so we can use that known information about the way the distribution shape looks to come up with some formal decision rules. Now, these next two statements are really important. When we've conducted our test, we reach a conclusion, and we can either say two things. We can either say we reject the null or we do not reject the null. Okay, so you have to get in the habit of thinking about those. We do null hypothesis testing, and we either reject the null or we do not reject the null. All right, the language is clunky, I agree, but they're the phrases that we need to use. And then the final step, which is the most important step in all of this, is to go from the test back to what was the real context or the question that you were looking at. So rather than just do lots of tests, we've tried to set up some context for the tests. So, and there are a whole range of majors taking this unit. So a few people in a quantitative sciences major might be taking this unit, but the vast majority of people in the major will be in some core discipline area. So you want to learn about, or for those people, you want to learn about statistical tests as they might relate to your core research area of interest. So I've just got some examples that we might be thinking about here. If you're more in that sort of geology, physical sciences space, you might be thinking about, things, mineral applications. So we might be looking about the quality of an ore body, or we might be looking about the energy content of coal delivered to a power station, or the ash content of the coal, those kinds of things. If we're in natural resource management, we might, be sending stuff to laboratories to get analysed, and we might need to interpret those applications. In the water space, so for example, in Shenton Park, we have a wastewater treatment plant. There's also a wastewater treatment plant down in Albany, but the output of those water uses are a little bit different. But the one I know quite well is the Shenton Park wastewater treatment plant. So after the water's treated, it's discharged into the ocean, and we monitor the outfall. So we want to have we want to be very clear about what's in the water that we're releasing into the environment, and we have some environmental standards that we hold Water Corporation to account to. So, these are things that we want to conduct tests because we have some area of interest. And really, for me personally, in the space that I work in, it's really a lot around the economics and the science policy interface. So it's those regulation questions that I work on. Now, to answer these questions, there are actually two fundamental types of techniques that we can use. We can use what are called parametric methods of investigation or non-parametric methods of investigation. So what is the difference between these two? Really, you can always use non-parametric methods, but if the assumptions for the parametric methods are valid, then these have more power to detect a difference. So if we think about the things that we're interested in, say we're monitoring some environmental site, we would like to be able to detect a change in conditions if there truly is a change in environmental conditions. And one of the things about parametric methods is if the assumptions are valid, they will have a greater power or greater ability to detect a difference in that change than non-parametric methods. So if the assumptions are valid, it seems always better to go with the parametric method. Now, the parametric methods rely on an appeal to the central limit theorem. So we're going to see how the central limit theorem works in practice. We're not going to derive any of the properties of the central limit theorem, but we're going to use some simulations to see that, by a simulation, demonstrate that these properties are true. And hopefully that will be sufficient demonstration to you to go, okay, yeah, I've seen that this thing really does work. It seems a little bit strange, but I've seen it in action and it works. Non-parametric methods work when the assumptions that we need don't work. And really this tends to be when we can't appeal to the central limit theorem, which means that we have a relatively small sample. There are other occasions when non-parametric methods might be valid, but generally these are the types of cases. So we have a very small sample and we have a clear understanding about something about the shape of that very small sample. So we will be exposed to both. Most of the analysis that we do will be parametric methods, so that's going to be the core. But because in the sciences you do see non-parametric methods used, we're going to also cover the equivalent versions of the parametric methods in the non-parametric framework. So that's what we're going to be doing. So we're going to start off though with our parametric models. So what we're really interested in doing with these parametric models is we're interested in making statements about underlying populations. Now, the reality is that we never measure all of the observations in the population. We only ever take samples. So from our sample, we get a guess of the population mean and standard deviation. So we're interested in a population. We never have the time or the money to take all the measurements from the entire population, and we take a sample. And from that sample, we can then use that sample information to make a guess about the population mean and the population standard deviation. And so we're going to have a look at how that works in practice now, and editing hopefully will work. So what I want to demonstrate here is the idea of taking a sample from a population. So in this setup here, I've got my population as being 60 farms. Usually the population is going to be something much bigger than that, but what I hope you can also see here is that we've got the population parameters. So we actually know what the mean and the standard deviation is for this population. The mean is 2.47 and the standard deviation is 0.98. So what I'm going to do is I'm going to take a random sample from this, and you can see these are the observations that I've drawn out randomly from this population. So I've gone out, taken a sample, I've interviewed a small number of farmers in this region, and then I take the mean of my sample, and you can see it's 2.5, and the sample standard deviation is 0.22. So they're a little bit out from the true population parameters, but they're not that far out. So let's see what happens. So I could have taken another sample. So let's say that I do this again, and I go out, take another sample. So I've randomly gone out and selected some farms to sample, and this time you can see that the mean 2.5, the sample standard deviation 0.13. So you can see they're a little bit more clustered together than what we have out here. But my sample is giving me a reasonable guess of the population parameters. So let me just do that one more time. So I go out and I take a sample, and this time I've drawn from this population up here. So this is my population. I've drawn my sample. From my sample I get an estimate of the population mean. So my guess from this sample of the population mean is this guy here, 2.57, and my guess of the sample standard deviation is 1.96. So you can see in this case the standard deviation is really quite close. So that's the idea. We can never really observe the full population. We take samples. When we have a sample, we use that to guess the population parameters.